So why can gravity make one distant supernova appear in 4 different places in the sky and even show up on different dates when light is supposed to travel in straight lines? Astronomers have watched that replay happen. A supernova is an exploding star, yet in some telescope images, the same explosion shows up as several separate points of light. In basic physics, light travels in straight lines through empty space, and a photon, the smallest packet of light, has no rest mass, meaning it isn't something you can weigh. In Isaac Newton's force-based gravity, massless things should not be pulled. But during solar eclipses, starlight passing near the sun is measurably deflected, so gravity is influencing light anyway. The question is, what influencing means if nothing is grabbing the photon? Gravity, in Einstein's theory of gravity called general relativity, is not mainly a sideways tug, it is a change in the geometry of spacetime. Spacetime is just the combined bookkeeping of where and when, because clocks and rulers do not behave the same in every situation. A massive object changes the measured distances and the ticking rates of clocks around it. That pattern of changed measurements is what we call curved spacetime. Free-falling objects then follow the straightest possible routes allowed by that geometry, called geodesics. Light follows geodesics too, so a beam can look curved on a flat diagram even while it is locally taking the straightest path available. That reframes the puzzle. Gravity bends light by reshaping the notion of straight. But how do we test curved spacetime instead of just telling stories about it? During the 1919 solar eclipse, stars near the sun's edge appeared shifted by about 1 3/4 arcseconds, an angle like a dime seen from a couple of miles away, matching Einstein's prediction. Modern measurements using radio signals from distant quasars, extremely bright galactic cores, confirm the same deflection with much higher precision. General relativity also predicts a timing effect. Signals that pass near the sun arrive a little late because their path is longer and because time runs more slowly deep in a gravitational field. That extra lag is the Shapiro time delay, and it is observed in radar links to spacecraft. Bending plus delay tells you light is responding to geometry, not to a hidden photon mass. Scale that sun, test up to a galaxy, and the same effect becomes dramatic. Gravitational lensing can split one background object into several images. The foreground galaxy, or cluster, acts as a lens because its mass curves spacetime and redirects light into our telescopes. With near-perfect alignment, the images can stretch into bright arcs or wrap into a circle called an Einstein ring. Here's the genuinely strange consequence. The multiple images don't have to arrive together. Different geodesic routes can differ in length and in Shapiro delay, so the same explosion can appear, fade, and then appear again in another location. In the Supernova Refsdahl system, astronomers used a lens model to predict the date a delayed image should reappear, and it did. The replay is a direct consequence of gravity bending both directions and times. So, what if most of the lens's mass is invisible? Can bent light map matter we can't photograph? Dark matter is the name for that unseen mass, inferred because galaxies and galaxy clusters have more gravity than their stars and gas can provide. In weak lensing, the bending is too small to make obvious arcs. Instead, many background galaxies are sheared, subtly stretched in a preferred direction. By averaging over huge numbers of galaxy shapes, surveys reconstruct where the mass must be, even if it emits no light. In the bullet cluster collision, lensing maps show most mass separated from the hot X-ray gas that contains most normal atoms, which is strong observational evidence that dark matter is real and does not behave like ordinary gas. So the same mechanism that bends a supernova image also lets us weigh the dark universe. The resolution is that gravity makes light curve because light is always taking a straight path, just a straight path in curved spacetime. A galaxy creates a geometry where several geodesics connect the same supernova to the same telescope. So multiple images are not errors, they are different legitimate routes through spacetime. Those routes come with different travel times, so one event can reach us on different dates without any signal outrunning light. When you hear gravity bends light, the precise claim is that mass and energy reshape the ruler and clock structure of the universe, and light follows that structure. That is why gravitational lensing is both a visual spectacle and a measuring tool for galaxies, clusters, and dark matter. Like if this was interesting, hit the subscribe for more and turn that notification bell on.